Part 4, here we go. So last thing I want to look at, I tried to show you some really common scenarios, and this is the last scenario that's like a really common thing that you need to see. And so here we've got an object on a ramp or an inclined plane. All right, to be a little dull about it, an inclined plane. And we're going to have some friction between a block and the ramp. The ramp's set at 30 degrees, just like that. And you can see the values for static and kinetic friction there. All right. So the first question I want to think about is, given that the angle is 30 degrees and that the static friction is 0.8, is that enough friction to hold the block up? Or will we have a case where we set the block on it and it just immediately starts to slide down? Okay, so let's address that first. Is that enough friction for that particular angle? Okay, so following our formula, all right, step 1, we're going to look for our forces. Okay, and the normal comes perpendicular to the surface, so it comes out like this. And then the only other force we have acting is our static friction. Okay, now let's transfer those to our free body diagram, and you can see there that the little twisted crosshairs, I'm using a free body diagram that's tilted, and I tilted it to match the tilt of our ramp. Okay, and what that does for us is that means our friction is here, our normal force is here, and then our weight is here. Okay, all right, so that's the weight, and that means we could call this component, this is the y component, but I like to call it the perpendicular component. And then here's the x component, which I like to call the parallel component, just like that. Okay, so I've broken those things up. And so with my two equations, I'm getting ready for step 3 on my recipe. With my two equations, I'm looking at fx's and fy's, and I could think of those as f parallels and f perpendiculars if I wanted to. Okay, we could do that too. All right. Well, let's go ahead and start in here. In terms of fx, I've got the parallel component of my weight is negative, and my friction is positive. Okay, so what that tells me right away is that my parallel weight, all right, is going to have to match my friction. All right, in order for this thing to be in equilibrium, those two things have to match. Okay, let's scoot over and look at our vertical information. Vertically, then, what we're going to have is the normal force is up, and my perpendicular component is down, like this. So my normal force is the perpendicular component of my weight, and that is the weight, mg, times the cosine of my angle. Okay, now remember, over here's theta, here's theta here. Okay, and you don't want to have to stop and think through this every time, so just memorize that. Okay, the perpendicular one goes mg cosine theta, the parallel one goes mg sine theta. Okay, so let's do that. I feel like I'm gonna need more room here. Here we're going to have mg sine theta, okay, and that's equal to fs, and there we go. Now fs, it's static, so it's not going to be equal to something, but it's bounded. There's a maximum for it, so we put less than or equal to mu s times the normal force. Just like that, okay? But we found that the normal force here is equal to mg cosine theta. Okay, so I get a new equation here. Okay, let me write it all in one line here. mg sine theta less than or equal to mu s mg cosine theta. Okay, and this is kind of cool. This is really interesting. The m's cancel and the g's cancel. So it doesn't matter what planet you're on. G's went away. It doesn't matter what your mass is. It could be a big, honking, huge, massive block, or it could be a pebble. It doesn't make any difference. Okay. We ultimately get this relationship involving sine, mu, and cosine. Okay. Now, if we do just a little bit of rearranging on that, take my cosine to the other side. Okay. I've got sine theta over cosine theta has to be less than or equal to mu s. Okay. Sine over cosine is tangent theta. Okay. So let's look at the tangent of 30 degrees. Okay. The tangent of 30 degrees happens to be 0.577. Okay. And so what our equation here is saying is, so we're comparing 0.577 and saying, is that less than or equal to mu s? And mu s was 0.8. And the answer is yes. Okay. It certainly is. So that tells us that we could stick this block on our ramp there and it will stay. It's not going to go anywhere. Okay. It's just fine. Okay. But let's suppose it's sitting there and we give it a little tap. Dip, dip, dip. Okay. And the tap is going to cause it to slide just a little bit. And when it slides, what happens is we go from mu of being 0.8 to mu of being 0.5. Here. Just like that. And so what that does for us is everywhere we've got the mu s here, okay, we could substitute in the value 0.5. Oop, not that one. Here, 0.5. Okay, and now you see if it starts to slide, we still have this tangent 30 term, but the friction is only 0.5. And so we have a situation where if we gave this thing a little tiny love tap, okay, it would just start to slide down the incline. Okay, as long as it's not being disturbed, it'll sit there on the incline just fine. Give this thing a little tap though, and it's just going to start to slide all by itself. Okay. Now, if mu were something else, or if maybe the angle were something else, we could have a situation where the block sits all by itself, and then we give it a little tap, and it scoots and then slows down and stops. Okay. But that can happen, but that's not the case this time. Okay. In this case, it's just going to start sliding, and it's going to go faster and faster and faster. Okay. All the way down the ramp. Okay. So, now let's go back to, I need to erase some stuff. Woo, I don't want to erase all that. Okay. Get rid of some things in here. Okay. I want to go back to my relationship here, where the tangent theta, depending on this guy. Okay. And how did that come back? Didn't I get rid of that stuff? Oh dear. Okay, anyway, so what I'd like to know is if my static friction is 0.8, how high can I set this angle in order for the, in other words, how steep can I make it before the block begins to move all by itself? Okay, how steep can I make that thing? And my condition for that becomes tan theta is mu s. Okay, and so our mu s is 0.8. Okay, so tan theta, and so theta is going to be the inverse tangent of 0.8. Okay, and we find out that our angle there is 38.7 degrees. Okay, and so with our coefficient of 0.8, we could leverage that ramp up higher and higher till we reach 38.7, and then our block is going to begin to slide. As soon as we hit 38.8, it's going to start to slide on us. Okay, just like that. Now, the maximum coefficient of friction that we're likely to have, okay, you don't usually get coefficients of friction greater than 1, but if we did have 1, okay, if the coefficient of friction was 1, then that puts us here, and that puts our angle at 45 degrees. Okay, just like that. So one of the things that's kind of hard when you're looking at roofs and highways and stuff, and you're or a roller coaster even, you're like, holy cow, this is so steep. It's always never as steep as your gut tells you. Okay, it's always less steep than that. Okay, if you're on a road and the road is, let's say it's a 10% grade, it's about 9 degrees. Okay, you will probably think you're gonna die. Okay, you think, oh, 9 degrees is nothing, but if you're on a 9-degree slope, you really are aware of just how steep it is. Okay. Anyway, roofs, typical roofs are, 30 degrees. A steep roof is maybe 40 degrees. That sort of thing there. Okay. So they're never really as steep as they look. People that do roofing on roofs that have very much pitch to them, if they're very steep, okay, they always have to use safety harnesses and little platforms for their feet and stuff like that, because you just can't get the friction. Well, the friction just, anyway, the system breaks down there, and friction's not going to hold you up. Okay, so let me zoom out on this one. Okay, and kind of hit it one more time. Okay, so again, identify all of the forces on your drawing, move those to a free body diagram, set up your X and Y forces, then work your algebra. Okay, on a test, completing these 3 tasks is like 80% of the credit. Okay, it's possible to get some algebra that's really gnarly and is maybe tricky or full of places to make mistakes. Okay, this isn't an algebra class. I'm not grading you on your algebra. You're expected to be able to do algebra, but everybody makes a mistake. So if you get those first 3 things done, you've got it set up correctly. At that point, the physics part of it is done. All that remains is the algebra. Okay? So anyway, there we go. Translational equilibrium. Okay. See you next time.